right. Rikard, thanks for joining us. And do you want to introduce yourself?
Yeah, I'm Rikard Hjort. I am a formal verification engineer with Runtime Verification and blockchain nerd.
Mm.
And day to day, I work on KWASM, which is our implementation of WebAssembly. So that's.
So when you say your implementation of WebAssembly, you who?
So runtime verification, or the K framework implementation of WebAssembly. So basically, it's a formal and executable specification of WebAssembly, written in what would look like a high-level functional language to many programmers, I think.
I see.
But it has some nice special properties. I'm sure we'll get around to talking more about it.
Cool. And Nikolai, what do you do?
Yes, I work at Near, helping with what we call Contract Runtime, which is essentially the way how we execute contracts, smart contracts, which are technically WebAssembly programs inside of our blockchain, and how we integrate it with what we call transaction runtime, which is essentially the part responsible for the functioning of the blockchain as a distributed database with consensus.
Cool. So yeah, I'm working also with Nikolai. My name is Max, on the runtime, which, as he said, includes execution of the contracts. Also trying to figure out all possible safety aspects of our runtime, because safety is incredibly important for the blockchain. You kind of can live without liveness. If your node stalls or crashes, it's okay. You can just restart it, have some social consensus about things, when to restart the nodes or whatever, get a new binary version. But if your safety is broken, it can be fatal for the blockchain. And therefore, it's mine and Nikolai's huge focus in our contract runtime and transaction runtime on how do we make sure the contracts execute deterministically and execute correctly. That's what we're going to be discussing today. So I'm going to let you guys kick it off. And
actually, I think it would be very nice before we start discussing like particular technologies such as WebAssembly or formal verification of runtime verification as a company, to discuss a little bit background ideas like mathematics behind that, the reasoning behind the formal verification. So Rikard, what would you like to share?
Well, in essence, I think a good way to describe it is that formal verification is a process which takes, I can write a bit, it takes a program, you take a program P and a specification S.
Are you writing somewhere?
Yeah, can you see it in the whiteboard?
Oh, now I can. Wait a second.
Great.
Yeah. Mm-hmm.
And you put it through this in typical programming fashion, magic box, and out comes either a proof that the specification holds or a counter example. And in theory, that's what you want, but in practice, there's also this slight possibility that we often don't talk about, that you can report, we could neither find a counterexample or a proof. But in principle, you formulate something you want to hold of your program. For example, if it's a token contract, it could be the number of tokens is constant, or no one can have negative balance. And then you give the program, the contract as input, and you ask a system to prove that this is true or come up with a counterexample. And you often end up in this kind of don't know phase. So this box here often requires some manual intervention. And that's what formal verification engineers spend a lot of their time on.
Mm-hmm. And what is the language for expressing P and S respectively? So how, I think for P it's mostly like predefined and depends on the area where you essentially perform the formal verification. But how do you formulate S?
Well, I mean, there are many ways to formulate P as well. I mean, you can say, well, it's just a program, but the thing that is, so I'm going to say it's implicit in all of this, is that there is this semantics that goes into the box. And that's one way to express what a program is. So essentially, it's like you define the world of all programs in a language. So that could be Rust or WebAssembly or what have you. And then your program is just a specific element in this world of languages. But to do formal verification, you need to express this language L in a mathematical fashion. And that's, for example, the WebAssembly implementation I'm working on is basically a way of turning the WebAssembly written, admittedly mathematical specification into another mathematical specification that we can run with our system. So the way you express S depends on how you have expressed the language L, or rather like how you express this world around here. So you usually don't just give the program as source text into this system, or you can, but the first thing that is bound to happen is that the program is turned into this mathematical object. And for example, we use something called matching logic. So you write your specifications in matching logic. If you're using a tool like Isabelle Hall, you will have an Isabelle Hall model of the language, and you can express things in regular higher order logic, or it could be first order logic. It depends on the tool, and the best way to come up with or finding a good balance between powerful specification languages where you can express a lot of things, and but you don't want to be able to express too much, because if you have a too powerful specification language, then verification can become harder. So there's a balance to be found there, and there's also obviously a user experience aspect to it, where you want to find a way to express specification that makes sense to developers. A very easy way could be to have assertions in your code and then just have the tool transform those, or transform the specification into, or write a specification for you that basically says, we're never going to revert because of an assertion. But you might want to express temporal properties as well, like say, well, if you ever touched this variable during a run of the program, you are not allowed to touch this later. And that can be harder to express.
But doesn't it actually mean that in a good case of formal verification, P and S better be the same, because like programmer shall express his or her desire in a program, and a part of those like desires, intentions, logic, you also express the invariants. So, for example, assert, as you mentioned, is a very simple form of the formal runtime verification. So, why do we want to go beyond asserts?
Well, first of all, like I personally agree with you. Like, and a big part of making formal verification more widespread is to make sure that it has good ergonomics for developers, and systems where you can use asserts or do like write annotations for like pre and post conditions, for example. That usually makes more sense for the developer. The problem is that if you want to do source level verification, or like, if you just want to have the developer, as they're writing code, also, write specifications, that's often a good thing, but there's not necessarily a big chance that the automatic formal verification engine is going to be able to prove that. And if you're a formal verification engineer, you usually know your tool, the engine you're working with pretty well. And some ways of formulating specifications are more amenable to verification. And you might want to like take this high level specification and break it up into many different smaller sub goals that you want to prove, for example. And then you need to have a language to express it in. I mean, it's the same thing. If you write, the first thing that happens to the program is that it will be expressed in this mathematical specification of the language. If the specification is also part of the source code, then the same thing happens with the specification. The specification is derived from the source code, but the first thing that gets put into the actual formal verification tool is going to be this. It's going to be written in some specification language that is usually more powerful. And you want, if you're doing formal verification, you probably want to be able to write your own specifications that you don't have to go through the source code to implement.
But actually, like if we talk about languages, I think usually there are like formal languages in the form of a formal grammar standing behind the language, and that's kind of one layer of languages. But actually, with languages, there is associated runtime semantics and certain behavioral characteristics. And the question is, which part of the language is actually to be addressed by the formal verification? Is it runtime behavior? Is it like certain syntactical properties of the language?
Well, I can't really think of anything that would be all that interesting to verify just using syntax. I mean, usually most languages try to have a very like straightforward and not too complex and undecidable grammar. Like if you want to write a parser, you'll write an LR1 parser, like that's parsing techniques. But then to give meaning to your language, that's sort of where the magic happens, so to speak. And that's also, where languages become more equivalent. Any Turing complete language is essentially, are essentially the same to some extent. And the way you define what each construct in the language does, I'd say that's the more interesting part. I mean, I'm thinking whether there's something that could be very interesting to verify as like what a programmer usually thinks of the pure syntax. But I mean, if it's rejected by the parser, then you're probably going to have a parse error and resolve that. And that's, I mean, the parser is a verifier. It verifies that what you're giving it is something that is expressible in the language syntactically. And the type checker is a verifier. It verifies that you are not doing anything that's considered illegal by the language's type system.
Yeah, that was exactly my point. Yeah. Okay. So like on a different layers or levels of the language, there are different rules. Like on the lowest level, there pretty much syntactic rules of the formal language. On the level of the type system, there are different computation essentially expressed in a type system, and I think a significant part of the language research, during the last 50 years, was put into essentially making a type system such that most of the semantics are actually caught on the level of the type system. And
right.
And so my question about like the formal verification as a technique is essentially how it augments the research, because like everybody knows how to write parsers. Many people know how to do like a type system and how to perform type checkers on lattices and so on. But I think not so many people, at least not myself, are aware how to go on the next semantic layer, which is higher than a type system. So how to express formal statements in that area, which builds like a complete axiomatic system, which could be actually used for as input for any like reasoning machine, which any formal verifier is. And so that's pretty much my question.
Just so I understand you correctly, you're trying to like figure out what's the gap between, you know, the type level kind of verification that a programmer is expected to do and what the things that we usually call formal verification, where, you know, you hire a formal verification engineer to prove properties of your program. I mean, really?
Yes, pretty much. It's like, it looks more like for example, type verification is absolutely like mathematical procedure. It's an algorithm. Once you have a described system for the language, and it's usually in some form is formalized as a part of the language, you can verify that the type attribution is correct in a particular program, and that's a mechanical process. And you don't need any additional operation, and it's not important if the program like on the same language. If it's like a word processor or web server, the type system manipulation will be exactly the same, and because it's a compiler and which does the verification. And so my question is, imagine if you have a formal verification, or what is the formal system against which verification happens? So like how it could be built, how it is built in your tool or in other tools.
Well, so in our tool, it's built through something called matching logic, which looks fairly similar to most logics that people may have encountered, but it's slightly more expressive. But say, for example, in Isabella Hall, you are using a slightly more familiar, probably higher order logic to express the meaning of programs. And I mean, it's not really the type system, and like these kind of formal verification things we generally do are not really in competition, because the idea with the type system is usually that it's supposed to be fully decidable. Like, I mean, it should be pretty straightforward for your type checker to just say this is well typed or it's not well typed, and might do unification, like, oh, you're doing addition, and you know it's going to see that, you know, one. Use actually this a good whiteboard moment. Like if you're doing 1 + 1 somewhere in your program, or rather if you're doing like P plus Q, and the type checker can infer that this is an int and this is an int, then you know this expression is well typed. But for that the type checker must be able to infer the type of every expression in the program, which puts a limit on the type system's expressiveness. If you want to have a type system that can express anything, then you move into undecidable territory. Now type checking becomes undecidable. And I mean, this limitation here that you will sometimes end up in don't know, that's just like a sort of mathematical threshold you cross. At some point, things are no longer decidable. Decidability means there is an algorithm that can decide this and will always be successful. Regular type checking in something like Haskell or Rust or Java is decidable because the type checker will always succeed to tell you whether your program is well typed or not. But if you want to have a slightly more expressive logic system, things become undecidable.
So a question, you're saying it's undecidable when it's theoretically undecidable, not something that your tool cannot infer because of some computational limitations.
Well, I mean, obviously, like there can be computational limitations. Like, I mean, there is definitely a. I mean, in practice, for example, I think in Isabelle there's a tactic that I think is called BLAST, which is technically, you know, it can take certain, I think, linear formulas, it's called, and do and check if they are true. And it's like sorry, I lost the word. It's not. Is it? You don't say that it's complete. Well, you know, it should always succeed in theory, but in practice, there's obviously a timeout limit. Somewhere the tool can give up. But there is also.
You mean the halting problem in some form?
Exactly. The halting problem is like the example that you know. Like if I give you the simplest, if I make the simplest Turing complete language, or if I give you lambda calculus and say, well, you know, will this program ever terminate? For a great deal of programs, that's pretty straightforward. But there are going to be some programs where it's not straightforward. So for example, and I mean, people often confuse this and think that, oh, you know, the halting problem is undecidable, therefore they can't be, you know, it's meaningless to try. But honestly, in many cases, I mean, if you're writing a smart contract and your contract just looks like this, it's just like straight line code, then I can tell you, well, you know, and this contains no calls and no jumps, then I can tell you, you know, this is going to terminate. But if you have a jump in here, or you have a little while loop all of a sudden, then it becomes more complex. Maybe I won't be able to decide whether this terminates or not. But the way many tools work is that they make sure that you, when you write like certain functions, for example, in Isabelle, you also have to provide a termination proof. But if you just define your functions using certain simple structures, then the program can automatically tell you, yeah, sure, this is going to terminate. And if you want to do something more complex, then it's your job to also provide a proof.
So the loops also include like loops in, let's say, standard arithmetic operations, mathematical operations, like let's say hash computation, right? Or like signature computation. I mean, like if we use it somewhere in our code, then we might end up in this do know state.
What was your example?
Well, I mean, let's say we have like a very simple example that our program verifies certain hash or like certain signature, right? And like we want to prove that the assertion that says the hash doesn't match never fires in the program. And so we cannot really prove it for the input because you need to literally pre-image the hash, which right. But like hash, but this is like an example of like a very simple program where you just have a hash computation, and you just cannot prove that the program will not panic because the hash has been like one-way function is being used somewhere in the code. But those one-way functions are like incredibly popular in smart contracts. Even like basic like asset manipulation, like DeFi contracts. So wondering whether if someone drops in this kind of like crypto function, will it automatically, you know, make it unusable, the formal verification unusable?
Oh no, and I mean, for example, I think you can scroll down a bit, Maxim. I'm just
Let me scroll down
below. There you go. That's my terrible. Like what you do in general. Let's see where you are. Okay. What we tend to do is like if we have. I mean, often you're doing something called symbolic execution, which means that instead of like inputting specific values into your program, you are inputting, let's see, there we go. You are inputting like a variable X, right? And so let's say your input to a program is X, and then at some point you get to a place where you do hash X. Oops. Mm-hmm. Since X is unknown, we probably won't be able to call this function. So what we'll do is we'll just leave the symbolic variable hash X here. And now we know certain things about this value, hash X. For example, it's between 0 and 2 to the power 256 minus 1 or something, right? And we also know that if you also have Y and you do hash, oops. I mean, because you're defining it as a function, and if you say, well, let's do hash Y, then we have the same situation. But now, if you ask me to prove, can you prove that hash? Oops, sorry, it's a bit of a lag on my end, so this becomes pretty ugly. If you ask me to prove, given that X equals Y, that hash of X and hash of Y are the same, I can do that because I just have that as an assumption of my specific hash function. I write like a lemma saying that, you know, this hash is correct. And that's usually what you do. I think it's Tony Hoare that said something like, the job of formal methods is to elucidate the assumptions upon which formal correctness depends. That's a fancy way of saying, well, the way you're doing formal verification is you're trying to figure out that something is correct given certain assumptions. So for example, if I'm verifying a smart contract, I will often assume things about cryptography because I'm not really proving things about cryptography, I'm proving things about the program. And I will say, this program is correct given that the cryptographic primitives are correct. Like, you know, if I do encrypt X with a key, it's a key, and then I do decrypt with the same key, I have a lemma saying, or like I have an assumption essentially saying, well, you know, that's going to be the same thing as X. If I encrypt it and then decrypt it and I use the same key, that's going to work. I will also have, or I might have a lemma saying the opposite, but you know, I mean, I guess there's usually a chance that there is some probability. The problem with cryptography is that it's very probabilistic. So for example, if I'm computing, if I'm storing two values, let's say X and Y are not equal, and you ask me, is HX equals to HY? The answer is maybe, unfortunately. We could just add as an assumption saying that, oh, you know, if X and Y are unequal, their hashes are not going to be the same. Basically, there are no pre-images. That's not true, but you can say that, you know, given that you're not getting a hash collision, your program is correct. And then you can decide, then you can employ your reasoning about that to say if that's good enough for you, for example.
If your data is longer than 256 bits, then for 256 bit hashes, you are guaranteed to have at least one collision. That's
yes,
like
exactly.
that's obvious. So
yes, I mean, so the point is, and that's why I come back to this Hoare quote, is that what you're doing is you're usually not saying, you know, this program will always work in every circumstance, because, you know, there's a physical world out there and things can go wrong, and, you know, is this going to work correctly given that every node fails in the same way at the same time? Maybe not. But you can, if you just have encode that as an assumption that, you know, your virtual machine is deterministic, or you encode as an assumption that you will never have a hash collision, then you can prove certain things. But that also means your proof doesn't work unless you state that as an assumption. And that's valuable, right? And you can remove that assumption and say, oh no, our contract works even if there are hash collisions. But either way, you can. I mean, you probably wouldn't state that there are no such thing as hash collisions, because that's patently wrong. You could use, like you said, the pigeonhole principle to prove that wrong, and now your whole system is unsound. But you could add an assumption saying, well, for these particular values x and y, they do not collide, and then you can prove that no one is able to steal your tokens, given that they can't produce a pre-image, for example.
And actually, I really like our discussion. However, it gets very very theoretical and probably close to mathematical problems, or even foundation of computations, let's say. So if we, I hate to be kind of a moderating person here, but I guess to make it more closer to the theme which we aim to discuss, we probably can discuss more like a practical aspect. So imagine that in our case, P is like a Rust smart contract. Could you give an example? What would be an S in your verification example, and how does it bring value to the a normal developer who's not mathematician, not formal logician, but like a smart person writing smart contracts?
Sure. I mean, if you're writing a program in Rust, and I mean, my standard example is it's a token contract, and I mean, history has proven that, history, like the last 10 years have proven that even something as on the surface simple as a token contract can have all kinds of really bad bugs in them. A program that looks super simple can, accidentally mint tokens. And so, I mean, that's an S that I usually take as an example, that in a token transfer, the outgoing sum of every address touched, or the outgoing balance of every program touch, is equal to the sum of all the ingoing balances. So if A on the inputs plus B on the input plus forever is equal to, if these are all the addresses that are sent as input to the transfer function, and these can be very complex. It can be like, oh, it's delegating to someone somewhere, and it's giving something to the contract owner address and whatever. But I can say that the ingoing transfer, or the ingoing balances, has to be the same as the outgoing balances. And I mean, this fails for all kinds of reasons. I mean, you could say you might, or the transfer might fail. An excellent example, of course, is overflow. I mean, if one of the addresses overflow during the transfer, then this doesn't hold. And so you might say that, okay, this is going to hold assuming that all the none of the addresses, there's no overflow in here, and you have to express that as a property, like assuming that the changes in balances don't cause overflow. This works. This is one property you want to hold. But another property you want to hold, for example, is that all the balances, all the out balances should be, Actually, let me do this by text. That's easier. So AI, B, I, etc. The outgoing balances are all larger than 0. or sorry, that the ingoing balances are all larger than 0, that's going to imply that all the outgoing balances are larger or equal to 0, for example. And that's another property you might want to prove. And from this, you might want to prove that, you know, the total amount of tokens in the contract is always the same. That might not be something you want. Maybe this contract is supposed to do minting. But I mean, from this proof, you might be able to extract quite easily the property like, okay, if you do a transfer, the transfer doesn't affect the number of tokens in the contract. And I think one way this can help a developer, and we often have this conversation, is like, how can we make formal verification easier? One way to make formal verification easier is to make sure you are always very explicit about your assumptions, and you try to like at least give enough information in your comments or your specification documents, or by the way you name things or whatever, that, or by assertions, that it make it look very clear that these kind of things can never be violated. But I mean, if you just write a straightforward transfer function, there are many ways that can go wrong. But if you write this down, these kind of specification, and then try to just look at your code, there's probably going to be places in there where this is violated, and then you need to start thinking, okay, am I sure that this is going to go back to a proper state? Like there's going to be somewhere where the value of A's balance has been decremented without the value of B's balance having been incremented, and so on. So I think like until we get, I mean, our tools are improving rapidly. We're in like a formal methods renaissance, but for the programmer on the ground right now, I think starting to become a bit familiar with formal verification and maybe with like property-based testing is an excellent way to make use of this right now. Because if you just start writing down your assumptions and your invariants, then you're probably going to catch yourself making certain mistakes, or end up. I mean, if you write down an invariant that's saying, like, for example, say you never want your contract balance you want it to be constant, and you just look over your contract and you're trying to like make sure that holds. If there's one function where you're kind of scratching your head and saying, oh, I'm not sure, but yes, I think I proved it. I think I thought it through once and it should work. Then maybe you can rewrite that function to make it clearer and convince yourself and others that it's correct. Mm-hmm. So I think the formal methods thinking and approach is valuable to everyone. And I mean, especially in the DeFi world where, you know, you have, sorry.
Yeah. I just wanted to say that it's like, what you described sounds like a very good hedging, which most good programmers I'm aware of pretty much follow, even without much of the training in a formal verification. So like, I know that good programmers writing complex systems always write asserts. So like checking your invariants frequently as possible is very common and very good habit. That's I'm fully agree. But this kind of gets back to the previous question which I had. So don't you really believe that the best practical formal verification is where at least languages for P and S coincide, or moreover, even where the P and S itself coincide? So where the formal verification must be a part of the program.
Yeah, I would even add to that, because I was going to ask in the same kind of lines the question that, you know, when engineers design a program and have invariants in mind, they enforce them through asserts, through the assertions, right? And the way basically the assertions that express the invariants is the S for the engineers. Like that's what I think Nikolai is going with, is that you have a program, right? You wrote a program, and then you go over and you try to make sure that the invariants hold, and your S is actually a set of assertions that you put in the strategic spots in your program. And,
for sure.
and since they have to do it like anyway, like good engineers, right? They need to be aware of the invariants and have to add the asserts everywhere. Where does the value of the formal verification comes in, since we enforce the invariants through the asserts? Like, why do we need to prove them additionally on top of that?
I mean, that depends. I mean, I guess there are two kinds of asserts. One kind of assert is like, sanity checking that everything works. And if it doesn't abort, like, checking, well, is someone trying to transfer money to themselves? Then, you can abort, for example, or that kind of thing. But another way you could use asserts that isn't really meant to be functional is writing down these asserts that should never be violated, and you believe that there is no way they can be violated. Those are the kind of asserts you probably want to remove at compile time. It depends, but I mean, those could cause your contract to DOS. Like, well, if you have an assert that you think can never be violated, and all of a sudden, that's say in the transfer function. And somehow you're wrong, and that ends up being violated. And the only way to modify it is by, calling transfer. Then, you're never going to be able to transfer anything with your token contract again. And now your token is worthless, probably.
Yeah.
So I say there are two kinds of asserts. Like people will often write assert, like sanity checking your input. Like, you call this thing correctly and you're not going to break anything. If that's wrong, we're just going to, if this is a theorem, we're going to eat your gas, or it's your problem. But that's input validation, and that's sane, and that's exactly like you're saying. Most good engineers, when they are not under the some certain very tight deadline or something, they should have those in place. But there are also the system invariants, and I think, I mean, I haven't been over all the contracts and all the different platforms, but I think those are usually not present as much. And those are really the kind of things you want. Like, you want to be able to say that your system will always be in this consistent state. Your deposit contract is never going to lock up. You're never going to lose these funds, or so on. And those aren't really like input checking asserts. Those are asserts of your system. And if those are violated, your system is probably designed around those always holding. And if those are suddenly violated, are you sure that you have the correct fallbacks for that? And I mean, and I mean, if that's all you take with you, like, oh, I'm gonna if you want to say, oh, I'm gonna show those formal verification engineers that I know need them, and I'm going to write asserts, and I'm going to say, well, if this invariant is ever violated, we're going to call the fallback function, and all our things are going to be liquidated, and everyone's going to be reimbursed. Then great, like, you've added some great panic handling, basically. But you did that by trying to think, what are the invariants I expect to always hold? Where can they be violated? Am I sure that I can handle them correctly? Because that's the kind of thing a verification engineer would find. Like, you assume that this will always hold. Well, it won't hold in this case. You say, okay, but in that case, I'm going to deal with it like this, and that's great. Now we have better software.
Well, yeah, and actually, in this regard, I have a related question. So because one of the I'm practical engineer in the sense that I did a lot of various complex systems, and it showed that there are two very powerful practical techniques for verification. One is assert, which I mentioned, and another is some form of a virtual machine, because you can put some invariant checking actually into your execution engine. For example, think for JVM, there is a formal verification of stack manipulation correctness, for example. So that it's a stack machine. So when you put values on stack and from stack, you essentially ensure that stack is balanced and properly typed. And similar thing exists in many other virtual machines. So So some invariants could be checked and ensured by the virtual machine. So what do you think formal verification could bring to the virtual machine? For example, if we have like wasm virtual machine, do you think there could be something which we could add to this virtual machine to execute smart contracts in a safer way?
I mean, what you're talking about, I mean, if I understand you correctly, this sounds like runtime monitoring, like checking that, you know, certain things, like checking at runtime that things always work, and maybe like executing this, exercising the system and running a lot of things and making sure that things always work. Is that correct?
Not exactly.
Like continuous
for example,
testing, or okay.
No. For example, if you look at the Java virtual machine, it has a bytecode verification. Bytecode verification is essentially before executing the code, the bytecode, you check that the manipulations with stack are correct, like balanced and so on. And
Sure.
And so there are other checks, like memory manager in a sense is something which helps perform verification, because it ensures that objects for which the reference are being held are not actually disposed, which could happen in language like a C or C++.
Right, and I mean,
so this
WebAssembly has similar things.
Yeah, sure.
Yeah, like
most
yeah, and I mean, those are properties that are super good to verify and are actually also kind of relatively easy to verify. Again, they're decidable. You can say that these, you can just look at a sequence of JVM bytes and say, okay, these are not going to violate, you know, cause stack underflow, for example. And that's because it's a decidable property. And it's also, you know, it's well known that that's something you can do if you just design your language correctly. But some things are not decidable. And especially like if you're an engineer writing contracts, it's very hard to design a general process that is going to check some meaningful property of every possible program you can construct. I mean, essentially, like formal verification is, you know, applying all these formal methods to the things that are not easy, or rather, I mean, the thing you're describing is also sort of formal verification, but it's the kind we take for granted. It's the same way we take type checking for granted. It's something we know how to do. It's something we can do well. It's something most people will be familiar with, and therefore we do it, obviously. There is no real such process for checking these kind of specifications of a token contract. If there were, we would just apply them, and every program on the EVM or the near virtual machine would, you know, be guaranteed to satisfy these properties. But since we don't have that, we need to do whatever we can, and that's usually takes some human ingenuity. And in 30 years, we're going to have a lot of cool new decision procedures to automatically verify a bunch of things that we think are important for smart contracts. But right now, you know, no one's thought of them yet. So what you're describing are a bunch of properties that are very important to verify. But there are other properties that are important to verify that are not as easy. It's sort of like in algorithms. Like, I mean, there's a bunch of algorithms. There's P and MP. Like, there's a bunch of things that are easy to do, and there's a bunch of things that are not easy to do. But the things that are not easy to do might still be important. Therefore, we're applying our ingenuity to try to solve them best as we can, even though we know that there are some, or okay, we don't know, but even though we think that there are some basic limitations to how well we can do it, we still want to do it. So even though we know that there is no decision procedure for whether a program halts, we want to be as good as possible in detecting halting. And we want to be as good as and automatic as possible in detecting important properties of smart contracts and when they're violated and when they're satisfied. And that's sort of where the research is happening.
Yeah, yeah, that's absolutely correct. I just wanted to like understand the practical consequences of formal verification for engineers. So, like, what would be the best practices? I guess we can understand one of the best practices, which is asserting. Other probably would be adding more checks into VM, but that's as you said, it's on a lower level, so it's less on the semantic layer and more on on just execution engine layer. And so if we talk about semantic related or formal verification, so what would you recommend people to do here, essentially? How to, other than think about before the program, which is probably very valuable suggestion, but still.
It's hard to do in general. It's sort of like saying, you know, what are the principles you should adhere to make good software? I mean, it depends on what software you're building. If you're building a website or you're building a nuclear missile launch system, you have different practices. And there are some things that are, you know, obviously always good, like, you know, document your stuff and think through things. And I think it comes down to being clever. Like, I mean, that's, you know, the keep it simple, stupid principle. Like, I mean, if you want to do something really, really clever, something that optimizes something in a really smart way, but that is non-obvious, you need to convince yourself and ideally convince someone else that this holds. So, I mean, code review is a great example. I mean, if you make sure you do good an honest code review, like people actually don't just, you know, let your stuff go through, like people actually say, I'm not sure this works. Can you show me and convince me 100% that it works? If you can convince them and you just like write that down in a comment or in a document somewhere, then, you know, you're essentially doing formal verification on paper. If you can write, I mean, mathematics is essentially writing convincing enough stuff. But also, you know, try to convince you. I think we often stop in this place where, okay, it's probably true, and I can't think of any way this would not work. Whereas, of course, verification deals with the problem of like, am I 100% sure this can never be violated? So, but I mean, and then, I mean, I also think one shouldn't be too hung up on formal verification as like, you know, the holy grail either. I mean, there are all kinds of things that are in between. I mean, in essence, you have like, let me grab the whiteboard again. You're gonna have this, let's do an arrow. Oh, it's very laggy, sorry. Let's see. It's a bad arrow. Like more and more better verification. And I mean, if you do testing, if you write unit tests and integration tests and everything, great. You've taken a step in the right direction, right? And if you do like runtime monitoring, or like, you know, you're always checking at runtime that things are working properly. That's a step in the right direction. And there's all these things that happen on this scale. And I'd say where the more formal verification stuff starts is things like bounded symbolic model checking, and say symbolic execution, like you find a symbolic execution engine and run your program on different inputs and try to verify things, or use, you know, state-of-the-art tools. There's every step to the right is probably an improvement, but I think we tend to get stuck in testing and then this fluffy thing, which is, just, oh, hang on. This is not going well. Here we go. This fluffy thing, which is hard to place on the scale, which is auditing, right? That's someone looking at things and saying, oh, this probably works and this follows best practice. I mean, one thing we're working on is trying to make a tool called Firefly, which focuses very much on using the existing test suite, like your existing program test suite and our formal methods to make sure that you've exercised every branch on the bytecode level. And we can also use that testing to do symbolic execution and check for properties getting violated. And you can write like invariants of your system, like saying my system should never violate this property. And then we can have that invariant, and we're going to keep it with us as we are running your test suite, and we're going to make sure that that always holds. So essentially, your test suite is not only testing the things that it's supposed to test, in a sense. It's also making sure at all times that all your system's invariants are not violated. And I think it's important to not get stuck in like full formal verification, because full formal verification is valuable, but it's also harder than these other techniques. And it's therefore, right now, it's sort of reserved for the most important things, the things that can absolutely never go wrong. Like, the beacon chain contract on Ethereum, like making sure that, that is going to work and making sure that certain properties hold of it. That's a good place to employ formal verification if you have the tools and the means. But it's not going to work for everyone at all times.
Yeah. Could you give like an example how, because this sounds like a super cool idea to what you just described, to actually take a test and essentially do like factorize it in a sense. So instead of actual values used in tests, just use equivalence classes of the text, which leads to same or different program behavior. Could you please explain how it works in the Firefly?
So I'm not sure I understand the question. You're saying how you can automatically generate tests, or how?
No, how could you translate tests from the actual execution to symbolic execution? I think if I understand what you described here, you essentially use a test as an input to symbolic execution engine, so that you kind of understand what's going on. Yeah. Mm-hmm.
Okay. Yeah. So I don't work on Firefly, so I don't pretend to be an expert on this. But the way I understand it is that what you do is we just have a specific contract, and if you are calling that within Firefly, we're going to catch that and give you a symbolic value back. Or initially, we're going to give you a random value back, just so you can do some random testing. But then we might also give you a symbolic value back. But if you run the same test in, say, Ganache, then it's just going to give you a specific number at all times, or maybe a random number. So the way I think Firefly does is like you ask for a random value from a specific point, and if Firefly sees you doing that it's going to turn that into a symbolic value, if I understand correctly. So essentially, like you have to write your tests, you write your tests as a property-based test, like a randomized test, and then I don't think this feature is fully implemented, but in the future, we're going to turn that into a symbolic, or we can turn that into a symbolic value, for example. But I mean, it's all just standard, programming tricks, using hooks and checking which environment you're in, and so I mean, formal verification is just it's very similar to programming. I identify myself as like a software engineer day to day, because like it doesn't feel that different. It's just working on a slightly different domain. It's like that I'm building the tools to do help specific development work, and I'm just doing it in a specific special language that has some neat features. So I mean, I think it's important that formal verification doesn't get stuck in an ivory tower of like, you know, I know I talk in very abstract terms sometimes because I want to make sure I stay correct and don't say things that are like provably wrong. But I think, I mean, a problem with formal verification sometimes is that it can be a bit too abstract. And I think what we're doing, or what I like to do, is just, you know, show the tools I'm working on and say like, hey, here's what this can do. And it looks like you're doing functional programming, which is probably not that scary. And it's something you probably should do. Like just kind of putting it in the hands of people and making sure, like I said, that people start thinking about, oh, I want to prove something. And then you start by saying, oh, what is you want to prove, right? Because people often come and say, oh, can you prove, I just want to prove that my contract is correct. And then you have to ask, well, what does that mean? What does it mean for your contract to be correct? And like, well, half the time people don't really have like, oh, but you know, I know what it's supposed to do. Well, you know, then it's doing what it's supposed to, right? I mean, unless you have something written down that you can check it against, you can't really do verification. And unless you have that, it's quite possible that you haven't fully thought through what your system is doing. And it's also even more possible that it's going to be hard for you to explain it to someone else.
So I have like a question here.
Oh, yeah.
Sorry, Nikolai. And that's also about the practical aspect. So we talked about the financial contracts here, right? Mm-hmm. And you might have heard that many financial contracts were broken or abused, not because you know, there was some bug in the code, but because people were able to find a way to combine them somehow together, or to do some manipulations on them in such a way that at the end they come out profitable.
Like Oracle manipulation and like with like flash loans, for example. Like
yeah, like flash loans, like yeah, whatever. Just like, you know, like some temporal manipulation. Like you can like, you know, like jack up the price, then you know, the dump it and all those kind of things, right? And
you can call out some other contract and manipulate the price as you're doing your thing.
Like even without going, you know, like in those areas where we talk about the cross contract, you know, interaction and everything, how would you go on with trying to prove that your contract cannot be financially manipulated, in temporal way, in such way that someone can somehow come out profitable at the end by just doing a bunch of like atomic operations on your contract?
Well, I mean, always start with the simplest way of doing things. And I mean, the simplest way of doing things would probably not be, you know, to do full formal verification on all the code and all the contracts. It would probably be something like set up a model, like just a little graph of the different contracts, how they interact. And again, like you have to come up with, well, like you said, how do you make sure someone doesn't walk away profitable? Well, how would you have to come up with a way to specify that. And it kind of depends on exactly what you're trying to specify. One thing you could say, like, for example, I don't know all these attacks in the specifics, but you'd say like, you want to prove that someone will not be able to manipulate the price of a Uniswap swap as they're, you know, in the body of the code, for example.
Yeah, I mean, like, sorry, I mean, like, before we go into the details, like, the reason why I like express this concern, because it sounded like, to me at least, this should be intuitively really easy to formalize. Something, you know, like something like a property of like some energy preservation thing, where you say like something that we were trying to talk about, which is like you cannot mint or like your total supply stays the same. Something right. in the lines of, you know, whoever interacts with the contract loses to the gas, or like always, you know, it's more like, you know, like some law of thermodynamics. If you interact with the contract, you always come out, you know, at least losing the assets for the gas.
Okay.
And it's and like in the direction you go in with is trying to say like, well, trying to formalize is too abstract, so you need to express more specifically what are the properties in there, and then try to prove formally that they hold. Well, what I'm saying, can we come up with some set of like almost like a laws of thermodynamics, but for the financial contracts that we can formulate overall for all financial contracts, and then just run verification independently of what is the body of the contract is?
That's a really cool idea. Yeah, I mean, definitely get a committee on that. Just like trying to figure out figure out the thermodynamics of financial contracts, and make sure that, I mean, since like I can publish a financial contract and it's turn complete and you can do anything. Not all contracts are going to adhere to it, but we can at least put down some best practices saying like all these things should always be respected by any good financial contract. That would be really cool. I don't know what that would look like, but it would be really cool, and it would, I think, definitely be amenable to formal verification. One problem with smart contracts is that they like to call out to other contracts, which is a good thing. It's composability, but it also means that you have to extend your assumptions to other contracts. So you have to say like if you're entering a specific function and that calls out to another contract, and you want to make sure you don't violate the laws of thermodynamics, you also have to assume that the other contract doesn't violate the laws of thermodynamics. But what if your contract call can be pretty complex? Maybe like there's, you're calling out to a different contract, and depending on, the world state, there are 4 different paths you can take, and each one of those paths call out to a different contract. All of a sudden, like now you have a pretty complex, you might come up with a pretty complex system of interacting contracts. And of course, users can define contracts to say, oh, please call this contract in the course of all this. And I think in practice, it can be hard to do that like at code level verification, unless like we have all the code, which we usually don't, because often you can call arbitrary contracts. It's usually not a whitelist that you can only call these. And that's why it's often good to model it in a more abstract sense, like make an abstract model of the system as interacting objects and so on, and try to work it out from there. And that's, I mean, definitely if you come from physics or something, then, or complex adaptive systems, then I think that's a great exercise. But then, it's also interesting, how do you bridge that gap? Because oftentimes you do verification at like a protocol level or a systems level. And well, what I do is usually I do verification at like the code level, and there's definitely room for error in the gap between those, where like you have some implicit assumptions in your big model, and those are slightly different in the code verification, and that can be violated. But basically, if you're expressing your system in mathematical terms. And doing some reasoning and proving things about your system, you're doing formal verification. And that's just the description of the action.
Yeah.
And whether it's useful or not depends entirely on what you're doing. Just like in math, you can do things that are not very meaningful, or you can do things that are really, really important. Like you can calculate, the triangular theorems in graphs that don't really have a strong application, or you can calculate, the stability of bridges and, security of financial systems and so on. So
actually, curiously, I have very similar question to what Max asked, just from another standpoint, but about exactly the same problem. I mean, when you started talk about formal verification as essentially mathematical modeling, I think humanity has very long experience of mathematical modeling, and especially in the area of physics. And in physics, we quickly realized, well, in any physics, like one of examples, I was thinking about like gas dynamics, for example, or thermodynamics, as Max said. It's the same. So you can, in theory, solve like dynamic equations for every molecule in air to essentially make a statements about like absolutely perfectly valid statements about the air around you. But that will be first absolutely understandable by a human who think about that. And secondly, it will be absolutely useless. Or you can say that it's like 25 degrees Celsius in this room. And it will be like very simple statistic property, which first makes sense and relatively easy, like measured and computed. So my point is that was exactly the same. So, but from human point of view. So if you make a validation of very complex software models, they became useless. It's very easy to make a mistake. It's not important how smart is a particular person. It just means that the complexity have to be like a little bit bigger, and the brain will break. Our brain is not that powerful technology,
Right.
so we have to simplify, and the trick here is other ways to not model, or not even precisely model, but quite the opposite, to model in a way which avoids the need to understand every behavioral aspect of the program,
Right.
but still be useful for.
Yeah, absolutely. And I mean, that's, I mean, if you're doing like protocol verification, that's often what you're doing. You just have actors that, or that way, that's more discrete deterministic thing. But again, like I'm not coming from the realm of physics, and like if you get a committee together and decide to work out like a theory of thermodynamics for these kinds of systems and a way to model, you know, your smart contract platform, where you can like look for these kinds of properties, that would be really cool. I'm not like, again, I'm not, it's not my area of expertise, so I'm not 100% sure what the use cases would be. I can imagine something like, okay, that would be great, like, you know, money, you know, value isn't destroyed anywhere, for example, or even if it moves around in interesting and complex ways, it doesn't like go up in smoke or so on. But all I can say to that, it sounds really cool, but it sounds really cool, and I hope you do it and get back to me when you do. But I also want to counter your point on saying, like, you know, oh, if you're trying to verify a system that's super complex, then, you know, the brain's going to explode because it's so big and it's so hard. I mean, that can be true, but I mean, verification, one of the powers of verification is that you can have very complex systems that do a lot of tricky stuff, and it's very hard to prove that they're right, but the statement of correctness can still be quite simple. Like a famous example is like the four-color theorem. So basically the idea that any world map or any possible world map can be colored in using only 4 colors without having adjacent countries having the same color. I mean, that's a layman's statement. The proof is immensely complex, like super complex, and it's been verified with like, you know, proof assistance. And but the thing is, the statement is pretty straightforward. And I absolutely 100% believe the 4-color theorem, not because I can understand the proof, but because I can understand at least somewhat the proof checker. And someone says, like, I have a long string of, you know, that represents a proof. We pass that through a very simple kernel that is a proof checker that only does like some very simple logic and won't allow you to do anything like obviously bad. And it's going to say in the end, oh yeah, I see you've actually derived this simple thing. You here, this is something that you have a simple statement, and I can attest to that this complex body that is the proof actually proves this theorem. And now we're done. So I mean, and your head doesn't have to explode around the theorem, even though like the proof, of course, took like a huge amount of people and a lot of years to work out. And I think that's one of the powers of verification, because we often talk about how like the number of bugs in code scale with the number of lines of code. And I'd say that, you know, the more complex your theorem statements are, the easier it is to make a mistake. If you have a lot of complex assumptions and complex encodings of state, then it's going to be easy for you to make a mistake. But oftentimes, your theorem statement can be quite small. And the process of verification is often taking these more complex statements. Like, for example, we did here with the transfer function. I mean, the statement, the transfer function, you know, doesn't violate the laws of thermodynamics. Like the amount of tokens stays constant or shrinks, or whichever one we choose. That's a simpler statement than saying every variable that is used somewhere in the body of the program has these properties at the input and output. I'd say that's the second statement of the problem leaves more room for error, but you can use that to then prove the bigger theorem. And I mean, that's pretty common in mathematics. You have to, if you're doing group theory, like Lagrange's theorem is really, really easy to state and prove. You can do it in a tweet, but you have to create this more complex body of other things first. But then the actual statement and the proof are pretty simple. And I think that's one of the really cool things about verification, is that you can kind of get this very high assurance because you have a very, very small statement, and you have, I'd say, absolute assurance that your statement is true. So,
yeah,
but I mean, yeah, I mean, but in practice, especially with smart contracts, you often end up saying, like, you know, well, this is true given these and these assumptions, because obviously it's a software system and it can be hard to encode these assumptions in an intuitive way.
Yeah, this sounds natural. Yeah, so I guess we actually already like 20 minutes behind our planned deadline. However, I guess we have very interesting discussion. I personally truly enjoyed it and like the ideas which we discussed here. And so I want to say thanks a lot to you, Rikard, to Max for joining this talk, and so maybe we can continue discussing these matters in some other format, because it seems to be very, very deep and very how do I say, strangely, it's very practical in a sense, because what we do, we all write a complex system, and we regularly and routinely verify them. So probably discussing it with from more like a distant point of view may be very very enlightening for any software engineer. So thanks you a lot. And
thank you, Nikolai. Yeah. Thank you, Rikard.
Thank you so much. It was fun.
Right. See ya. Thanks everyone for listening.